Hey guys, welcome to the Biomechanics 2 video series. We're looking at specifically the biomechanics of running and more specifically that of sprinting. In this case we are given some details around the sprinter that is set up in its starting blocks in terms of what their mass is and forces that the sprinter is exerting within the starting blocks, which are subdivided into forces P and Q, with a specific magnitude of 48 kilograms of force and 102 kilograms of force respectively, each acting at an angle of 28 degrees to the horizontal and 51 degrees to the horizontal. In this specific example, we are interested in what the magnitudes of the force with which the sprinter will be leaving the blocks, right, which will define as the resultant force, and we are also interested in the angle with which the sprinter will be leaving this specific set of blocks, right? So the direction and magnitude of force application is what we're trying to ultimately solve. In order to get this answer, we will use what is called the component method. This is just basic revision of aspects that we looked at in Biomechanics 1. As an overview, if I have a given force acting at some direction to the horizontal, we'll just call that theta, then we can see that there's an x component, a horizontal component which we'll call f of x, and there's a vertical component of this force which we'll call f of y. How do I calculate the f of x? Well, f of x is calculated as the magnitude of f times the cosine of the angle, whereas f of y is equal to the magnitude of f times the sine of the angle. Alright, so this is an overview of trigonometry, so if you guys get stuck and you don't know where the sine and the cos is coming from, there's another set of videos specifically dedicated to that. For now, that's beyond the scope of what I'm looking at here. We simply want to get to the answer for now. Alright, so if I know this particular convention, then what I'd need to do ultimately is to find all the horizontal forces as well as all the vertical forces acting or being exerted by the sprinter in order to find my resultant force and be able to calculate the angle with which the person is leaving. If I wanted to find the sum of all x forces or forces in the horizontal direction, what I'm essentially doing is finding the component of P acting in the x direction plus the component of Q acting in the x direction plus any other forces that may be acting in the x direction. If I look at the forces that I'm given, which are simply P, Q and W, this would be pretty much it. How do I know what to add and subtract? Well, by convention we have to specify this. Traditionally, anything acting up and to the right is given a positive value, and anything down and to the left is given a negative value. So if I want to calculate the component of P acting in the x direction, what I do is the magnitude of P multiplied by the cosine of its angle, and the same is true for Q. It's the magnitude of Q plus the cosine of multiplied by the cosine of its angle. And since both of these x components are acting to the right, which I can see here, I am adding them together, right? They have a cumulative effect. So then it's just a matter of plugging in the values. This would be 48 times the cosine of 28 plus 102 times the cosine of 51, right? Which gives me a value of 42.4 kilograms of force plus 64.2 kilograms of force. You might be asking yourselves, well, why am I not writing this in newtons? Why am I writing it in kilograms of force? Is that not an incorrect way of doing it? Well, in essence, what I would traditionally do is that you would take the kilograms and multiply it by 9.81 meters per second squared, right? Which gives you a Newton value. And at the end, if I want to find out what the kilogram value is, I have to take this value, this one, whatever answer I get in newtons, and divide it by 9.81, which gives me the kilogram value. So I'm skipping that and simply stating that I'm looking at kilograms of force, which allows me to get away or circumvent this expansion, even though the answers are by units more correct. So hopefully that makes some kind of sense, right? So this gives me a total force acting in the x direction, or the horizontal direction, of 106.6 kilograms of force. I do the same for my components of y, so I look at P acting in the y direction, the component of P acting in the y direction, the component of Q acting in the y direction, and any other force, which in this case would be W, right? So I haven't accounted for my signs yet. Remember, anything acting left, up or right is given a positive value, and anything left or down is given a negative value. So you'll see here that P is acting up, as is Q. So I have two components of the force that the sprinter is applying acting in the upwards direction, and I have this W acting in the negative direction. So essentially I would say add a negative W, which would simplify to P of y plus Q of y minus W. So it's simply the magnitude of P times the sine of its angle plus the magnitude of Q times the sine of its angle, right? Minus W. Well, since it's acting straight down, that is at 90 degrees, and the sine of 90 is equal to 1, correct? Alright, so I'm just leaving the sine out for now. It is therefore 48 times the sine of 28 plus 102 times the sine of 51 minus 70, which gives me the following values: 22.5 kilograms of force plus 79.3 kilograms of force minus 70 kilograms of force, and I have a final answer of 31.8 kilograms of force. It's still a positive value, meaning that my resultant component acting vertically will be positive, right? So now I have the two sides of my triangle. So the f of x is acting to the right with a magnitude of 106.6 kilograms of force. It is acting vertically with a magnitude of 31.8 kilograms of force, meaning that I can now solve for what my resultant should ultimately be, right? So my resultant, let me undo that for a second, that's a bit skew. So my resultant, once it decides to draw, should be able to get the magnitude and its angle given the two bits of information that I have now. How do I find the resultant? Well, I would use Pythagoras' theorem, right, which says that the f of r is going to be the square root of 106.6 squared plus 31.8 squared. Okay, which gives me an ultimate answer of, yes, give me a second, 111.2 kilograms of force. So I can plug that in, 111.2. So the only thing that I'm interested now is this angle. Well, I've got two sides and a given angle. Well, if I have this opposite and adjacent side, I will use tan. So the tan of the angle is equal to the opposite side divided by the adjacent side. And that means, therefore, the angle is equal to inverse tan, which you'll chuck into your computer, divided by, multiplied by the opposite of the adjacent. It's a simple matter of plugging in the values. 31.8 divided by 106.6, meaning that the angle is 16.6 degrees, which I can enter here. So that's my final answer. Good. In essence, in the real world examples of how I would do this, there are two ways to gain this information. Either I'd have to find out what the force application is on each of the starting blocks. So there are sophisticated starting blocks these days that can do that, right? They have little force sensors within each of these starting block components, and that can measure the amount of forces that the athlete is projecting in the direction in which the athlete tends to be projecting these forces, and then you can make some calculations in terms of what the resultant force application is, and ultimately what the acceleration of the center of mass would be in the direction in which that center of mass would accelerate. An alternative method is to do a frame by frame analysis, where you would be able to digitize the center of mass of this athlete, and you would be able to track this as the athlete stands up and is sprinting forward. You would find that you can track the center of mass, and once you can find the center of mass and how it tends to change over time, you'll be able to find the acceleration of the center of mass. Once you know the acceleration of the center of mass, you'll be able to find out the x and y components of the forces that are acting on it, right? So it's kind of using inverse dynamics in order to get to the same answer. It's a little bit more complicated, a little bit more cumbersome, because you need more information to do that, but that's in essence what we do here at the center, is to use inverse dynamics to find the magnitude and direction of force application acting on the center of mass over the number of steps that you can track the athlete. In any case, I'd like to leave it there for now. We'll use several more examples of this. For now, I hope you guys can get to grips with what the implications of this are, and how the calculations and the mathematics behind it all tends to work. Alright, see you guys later.